Today we resume our lecture video with antiderivative and integration. These two terms are basically the counterparts, or you can say the reverse, of derivative and differentiation. Which we have already learned before the midterm exam. Now, how exactly are these two related to these two? Let's find out about that in the next slide. First of all, let's assume that we have a function right here. Actually, it can be any continuous functions out there. For example, these functions down here. F of x, g of x, h of theta, that is fine too, with the theta. J of x, and k of x down here. But for now, let's call it f of x up here to keep it simple. Now, if I differentiate this function along this arrow, so this is diff. I'm going to get its first order derivative, which is f prime of x right here. As you can see, diff is the action and derivative is the product or the result. If I continue to diff f prime of x, so diff it right here, I get f double prime of x, which is the second order derivative of f of x. You can keep doing that. Keep differentiating this again and again to get higher order derivatives. So this one we have higher order derivatives. As a warm-up, let's differentiate these functions down here. Let's diff f of x right here. So we are going to diff this. And we get f prime of x. It's going to be equal to, so x to the fifth, power is going to come down, and power decreases by 1. This one is easy. What about the next one? Let's diff g of x. So this one we are going to diff and get g prime of x. Before anything, I'm going to change this to x to the power of minus 1 over 2. So once again, the power rule. Power is going to come down to be equal to minus 1 over 2, and power decreases by 1. So I have minus 3 over 2 up here. Let's continue. Let's diff this h of theta. So I get h prime of theta equal to, before anything, let's put this in a box, cosine of this box, theta over 2. So I'm going to apply the chain rule. So I'm going to diff the most outside function, which is cosine. I diff cosine, I get minus sine. So minus sine right here. And I keep the inside of the box the same, leave it alone. So I still have theta over 2 right here. And now I diff the inside of the box, diff this, I get 1 over 2. So I get 1 over 2 right here, and I multiply that to the first term. Next one, let's diff j of x down here. Diff this, you are going to get j prime of x equal to, first of all, let's take a look at the function that we have here, exponential of minus 3x. So I'm going to put minus 3x inside a box so that I can apply the chain rule. I'm going to diff the most outside function first, which is the exponential. You diff exponential, you get exponential. Nothing changes. E stays the same. And now the inside of the box is left alone. So I still have minus 3x right here. And now I diff the inside of the box, diff minus 3x, I get minus 3 right here. And multiply that with the first term. There you go. Now last one, let's diff k of x. Diff this, you are going to get k prime of x. Before that, I'm going to do this equal to 5 times x to the power of minus 1, which is the same as 1 over x. So this is basically the power rule. So equal to, the power comes down, it becomes minus 5 and the power decreases by 1, becomes minus 2. Or you can say this is equal to minus 5 over x squared. Now let's move back to our new term right here. What exactly is antiderivative? Well, it's basically the thing that you need to diff in order to get the regular function. So if you diff this antiderivative, you are going to get this regular function right here. So this is diff between them. What about we use this notation, capital F of x, to represent antiderivative of f of x. And if you diff this capital F of x, you are going to get the small f of x, the regular function. Now, what about integration, the second new term of today? How does it fit into this flowchart that we have right here? Well, integration is the reverse process of differentiation. It's going to be this reverse arrow from f of x, small 1, to the big F of x. So if you integrate small f of x, you are going to get its antiderivative, big F of x. This means that integration is the action, something you do, and antiderivative is the result, the product, between these two. When it comes to this integration process, you can apply it to this part as well, from f prime of x to regular f of x. If you integrate f prime of x, the first order derivative of f of x, you are going to get the regular function back. So that's basically it, the relation between function, diff, derivative, integrate, and antiderivative. Now let's try to integrate all of these functions down here. Let's start with this f of x. Let's find the antiderivative of this function, x to the fifth. And we are going to call it big F, capital F of x equal to. Now, since integration is the reverse or backward process of diff, we are going to do the same with our logic. We are going to apply the reverse logic of diff, which means that we are going to ask ourselves, what do we need to diff in order to get this x to the fifth? And we know that it has to be the same polynomial term, x to the power of something. For the power, it has to be increased or higher by 1, which means that we are supposed to have 6 right here, x to the power of 6. Now, if we try to diff this, 6 is going to come down. However, we don't have 6 right here, which means that we have to get rid of that 6 by dividing that number down here. Okay, now let's try to diff this. You diff this along this arrow. 6 is going to come down, cancel with this 6 down here. It's gone, and then power decreases by 1, so we have x to the fifth as the result of that. So this is diff. But what we just did is the reverse logic, which is the integration. Going from x to the fifth, right here, integration. Okay, let's move on to g of x. Let's find antiderivative of this function, right here. So we are going to call it big G, capital G of x, equal to, now we are going to perform integration backward logic of diff. So what do we have here? We have x to the power of minus 1 over 2. Once again, a polynomial term. So it has to be this x to the power of something again. Now the power has to be increased or higher by 1. It used to be minus 1 over 2, now it's going to be 1 over 2. If I leave it like this, if I diff this, 1 over 2 is going to come down, but we don't have it over here, 1 over 2. So I'm going to get rid of that 1 over 2 by dividing that number again over here. Now let's try to diff this term. 1 over 2 is going to come down, cancel with this 1 over 2 down here, it's going to be gone. And then the power decreases by 1, so we have minus 1 over 2, exactly the same as what we have over here. So this is also equal to 2 square root of x. Now moving on to the next function, h of theta. Let's find antiderivative of this function. Let's call it big H of theta equal to, now we apply the reverse logic, integrate this. Integrate what do we need to diff in order to get cosine of theta over 2? So we ask ourselves, what do we need to diff in order to get cosine? And as you know, we need to diff sine in order to get cosine. So definitely we are going to have this sine right here. And now we leave what's inside cosine and sine alone, so that it doesn't change. Theta over 2. Now let's try to diff this sine theta over 2. We are going to get cosine theta over 2. But with the chain rule, 1 over 2 is going to come out, but we don't have it over here. We don't have 1 over 2 outside, so we are going to have to get rid of that 1 over 2 down here. Divided by 1 over 2. Now let's try to diff this. Again, diff sine of theta over 2, you get cosine theta over 2. With the chain rule, 1 over 2 is going to come out and cancel with this one down here. So there you go, we have this cosine theta over 2. This one is also equal to 2 sine theta over 2. Now next one, j of x, let's find antiderivative of this function. We are going to call it big J. Capital J of x equal to, now we apply the reverse logic. We integrate this. And once again, we ask ourselves, what do we need to diff in order to get this e to the power of minus 3x? And as you know, we need to diff exponential in order to get exponential. So we are going to get this e again. You diff e stays the same. And we leave what's inside this power alone, minus 3x. Now let's try to diff this, big J, e to the power of minus 3x. So e stays the same, but with the chain rule, minus 3 is going to come down. But we don't have minus 3 right here. So we are going to have to get rid of that extra minus 3 by dividing that number down here. So let's try again. Let's diff e to the power of minus 3x. We are going to get the same e to the power of minus 3x with the chain rule. Minus 3 is going to come down and cancel with this minus 3 down here. So in the end, we are going to get this e to the power of minus 3x. So this is done. You diff back, you get small j of x. Now last one, we are going to find antiderivative of this k of x. And of course we are going to call it big K of x equal to, now reverse logic, integrate. What do we need to diff in order to get this 5 over x? 5 is a constant, so it stays the same right here. What about 1 over x? What do we need to diff in order to get 1 over x? And we know that we need to diff ln of x. So we have ln of x right here. So let's try to diff this. Let's try to diff 5 ln x. Diff ln x, you get 1 over x. And now you get this 5 over x back for the small k of x. And there you go, that's what you need to do in order to integrate a function. Since we already know how to diff, we just need to think backward. We just need to think, what do we need to diff in order to get the function that we have, so that we can find the antiderivative. Now let's move on to the next slide. Okay, what we have right here is the formula table for finding antiderivatives of different functions. For most of them, they are basically the same as the differentiation rules that we already know, except that we are doing it backward here. Let's take a look at the first one right here. Let's find antiderivative of x to the power of n. So this is the power rule in reverse. So we need to ask ourselves, what do we need to diff in order to get this x to the power of n? And we know that it has to be the same polynomial term, x to the power of something. And then the power has to increase by 1, and that's why we have n plus 1 right here. However, if we leave it like this, if we diff this, n plus 1 is going to come down. So we have to get rid of that by this division of n plus 1. And there you go, we have the result right here. Now, next one. Let's find the antiderivative of this sine of kx. So k is a constant and x is the variable. Now we need to ask ourselves, what do we need to diff in order to get sine? And we know that we have to diff minus cosine, and that's why we have minus and cosine right here. and then we have to leave the inside of this trigonometry function alone. K of x stays the same. However, if we leave it like this, k is going to show up from the chain rule. So we have to get rid of that by this division right here by k. Same thing with cosine of kx right here. What do we need to diff in order to get cosine of kx? So we need to diff sine in order to get cosine, and that's why we have sine right here. And we need to leave the inside of the trigonometry function alone, kx, so that it stays the same. And we know that with a chain rule, k is going to come out, so we have to cancel with that extra k with this division of k. Now same thing over here for secant square. We need to diff tan in order to get secant square. And once again, division by k to get rid of that k from the chain rule. And it keeps going. What do we need to diff in order to get cosecant square of kx? So we need to diff minus cotan. And once again, we have this division by k just the same. Same thing here. What do we need to diff in order to get secant tan? Of course, we need to diff secant, and same division right here. Last one, over here, cosecant and cotan. What do we need to diff to get these terms? Of course, we need to diff minus cosecant, and division is the same. On the right hand side, what do we need to diff in order to get this e to the power of kx? Of course, it has to be the same e to the power of kx right here. But with the chain rule, we need this division to cancel that k. Now, what do we need to diff in order to get 1 over x? Of course, it has to be ln x. You diff that to get 1 over x. Now, for these three, they came from the differentiation of the inverse trigonometry. So make a note right here. That is the same as diff of inverse trig function. Now the last one, exponential with different base, a. So this is the same as the differentiation of a to the power of kx, except that we do it backward here. So you can look it up on this one. As you can see here, we don't really need to memorize all of these because it's something that we already know, except that we do it backward in this table. Now the only thing that I purposely left out is this constant c, all of them. Right here, all the way down, we have constant c on every antiderivatives here. As you already know, if you diff a constant, it's going to go to 0. It's going to disappear. So if you diff this antiderivative, dc by dx is going to be equal to 0, gone. Which means that this c right here that we have at the back, it can be any constant. Once you diff, it's going to go away anyway. So let's make a note right here that c can be any constant. And this means that every time you find a general antiderivative, this constant c has to show up. It has to be there at every function right here. So don't forget about this. Okay, let's move on to the next slide. As many of you might already know that an integration of a function is related to the area under the graph of that particular function. Let's take a look at how we can estimate such area using simple geometry. On the left hand side, we have this curve of y equal to 1 minus x squared, or you can say that this is a function of x equal to f of x. And then we want to calculate the area under this curve in the first quadrant, trapped between x and y axis. As you can see here, the curve of this function is, well, curvy and nonlinear. This means that we don't have an exact formula built specifically to calculate the area of this region. So, no formula available. What else can we do? Well, we can start off by using estimation. The key is right here, estimation. Now, let's begin by splitting this region into 4 parts. The first part from 0 to 0.25 like this. Somewhere around here, 0.25 all the way up, cutting through. And now the second section from 0.25 to 0.5. Here, all the way up again. Now third section from 0.5 to 0.75, somewhere around here, all the way up again. And the last one from 0.75 to 1. So we have 0.25 right here and 0.75 over here. Now we are going to estimate the area of each section by using a simple rectangle. Even as simple as it sounds, we still have a choice to make here. We still need to decide which function value should we use as the height of the rectangle. For example, this first part right here, we can pick any function value along this small curve as the height of the rectangle that we are going to build. So which one is good? Let's find out. The first option that we have here is to use the left function value as the height of the rectangle, like what we have on the right hand side here. Here we have the left function value over here as the height of the first rectangle, the estimation of the first section. For the second section, once again we have the left function value as the height of the rectangle. Third section, once again left function value as the height. And last one, left function value as the height. So let's make a note right here that for this case it's left function value as the height of the rectangle for our estimations. Well, if we can use the left function value as the height, then the right function value should be fine too, and that's what we have on the left hand side down here. For this one, it's going to be right function value as the height of the rectangles. So let's take a look here. The first section, the right function value as the height of the first rectangle. For second section, right function value as the height. Once again, third section, right function value as the height. And last one, right function value as the height, even though this one is 0. Well, to think about it, if the left value is an option and the right value is also an option, it means that the middle value has to be an option too. And that's what we have down here on the right. So this one is going to be middle function value as the height of the rectangles. As you can see here in the first section, middle function value as the height of the first rectangle. Second section, middle function value as the height over here. Same thing down here, third section as the height, middle point, and once again down here, middle point as the height of the last rectangle. Now at this point, the question is which option is the best? So we have the first option, left function value, second option, right function value, and the last option, middle function value. So let's start with the first option right here, left function value. As you can see here, the rectangle, the first one, is larger than the actual region on this section. So we have overestimation. Rectangle is larger than the actual region. Same thing here, the second section, rectangle right here is also larger, so this is overestimation. Same thing on the third section. This is overestimation, too large. Same thing down here. The actual region is inside the curve. So let's make a note. Over here we only have overestimations. Only. At this point, you can calculate the area of each rectangle in this option. So this one is the area of the first piece, first rectangle. This one, second rectangle, third rectangle, and the last rectangle. And the total area from 4 rectangles is 0.78125. Of course, this number is going to be overestimation as well. Overestimation. Okay, what about we assign A1 to be the estimation from the first option? And since we know that A1 is an overestimation due to these extra areas that we have over here, this means that A1 is going to be larger than the actual area of the region R that we want to find, larger than R. So A1 in some sense is like the upper limit of the area of R, and we call it upper sum. Upper sum. Now let's move to the estimation in option 2, where we use right function value as the height of the rectangle. As you can see here in this case, the rectangles are smaller than the actual region. So over here we have underestimation. The region itself is larger than the rectangle. Same thing here, the region is larger. Rectangle is too small. Same thing down here. Underestimation all the way through. So make a note. Underestimation only for this case. And we can do the same thing down here. We can calculate the area of each rectangle in this option. Area of the first piece, second piece, third rectangle, last one. And the total from 4 rectangles we have 0.53125. And let's assign this value to A2, estimation from option 2. As you can see, all the rectangles are smaller than the actual region. This one is smaller, same thing here. Actual region is larger, same thing down here. This means that the value that we have down here, 0.53, is going to be underestimation. Smaller than it should be. And it also means that A2 has to be less than the area of the actual region R, less than R. In this case, A2 is like the lower limit of the actual region, so we call it lower sum. And now moving on to the last option, number 3, middle point. As you can see, all the rectangles that we built for these options have overestimations over here. First one, this part is too large than it should be. This is also overestimation, rectangle larger than the actual area. Over here too, too large. And then over here, too large. So we have overestimations. But not just that, we also have underestimation as well. So let's take a look here. This part, the rectangle is smaller than the actual region. So this is underestimation. And also this part, rectangle smaller than the actual region. Also here, rectangle smaller, and also here. So let's make a note for this case, middle function value as the height of the rectangle. We have both over and under estimation. So you can say that this leads to cancellation of errors, which is good. And now we can do the same thing. Let's calculate the area of each rectangle in this option. First rectangle, second rectangle, third one, and the last one. And the total is 0.671875. And let's assign it to A3. Now let's combine all of these values that we have up to this point. We have the upper sum as the first term. So we have A1 as the upper limit, upper sum. And we also have the lower sum, A2. Over here, lower limit. And we know that the actual area R has to be less than the upper sum and larger than the lower sum. Alright, what about A3? Where should it go? As you can see down here, A3 has cancellation of errors, which is a good thing, which means that A3 has to be in between A1 and A2 as well. So A3 in between A1 and A2. Now let's make a box around this. And now let us decide which one is the best estimation option to estimate the area of R in this case. Of course, we have to pick A3. The middle point should be closest to R. And we are going to use this type of estimation for definite integral. We are going to see that in the next slide. On this graph, let's apply the same concept that we just did in the last slide to estimate the area under this curve, this blue curve. Let's call it f of x. Starting from this point, right here, let's call it x equal to a. So we have this boundary. Until we get to this point, right here x equal to b, another boundary. First of all, we have to split this region into multiple sections. Let's assume that the first cut is right here at this point. And I'm going to call it x1, which means that the point on the boundary is x0. So over here at this point, x0. Now another cut right here. I'm going to call it x2. Another cut right here, x3. And it keeps going until it gets somewhere over here. I'm going to call it xk. K can be any value. And it keeps going again until it gets to the last point right here. Let's call this point xn, which means that the point before that is going to be x of n minus 1. Which means that we can have all these lines to separate all these sections. First one right here at x1, straight through. Another one right here. x3, one more right here. xk keeps going. xn minus 1, there you go. From the previous slide, we learned that using the middle points is supposed to be the best estimation that we can have. So let's start with the first section. C1 that is already there is not really in the middle, so I'm going to move it to right here, right in the middle. Let's call this point C1. And C2 right in the middle, right here. Same thing here, C3. And keeps going until at this point CK. And keeps going right in the middle again, and right in the middle here. And this one is going to be CN, the last middle point in the last section. Now that we have all these middle points, we can find the function values at these points. So the first one, C1, let's find the function value. Should be around here. So right here, it's going to be function at C1, the first middle point. At C2, the function value should be around here. Okay, let's make a note right here. Function at C2. Same thing with C3. Function value around here. At this point, it's function value at C3. And now at CK, right here. Function value around here. This one is going to be f at CK. And now last one. Well, this one is not really in the middle, but it's okay. You got the idea. So this one, go up to get the function value, and this one is f of Cn, last point. Now that we have all these function values in our hands, we can attempt to calculate the area of each rectangle in each section. So let's start with the first one on the left-hand side. The first one should be this rectangle. Should look something like this up to here. And now we know the height of this rectangle, which is f at C1, the first middle point. So let's write it right here. F of C1 times the base of this rectangle, which is x1 minus x0. So let's put it right here, x1 minus x0. And that is the area of the first rectangle. Now we move on to the second rectangle. It should be this one right here. Starting from the base up to this point, something like that. Now for the height of this rectangle, we know it's the function value at C2, the second middle point. So we have it right here, f at C2. Now for the base, times the base is x2 minus x1. So put it right here, x2 minus x1. And of course, we need to sum them together. We need to add all the pieces. And it's going to keep going until we get to the term k. For that one, it's going to be this rectangle. This one right here. Something like that. The height of this rectangle, of course, is f of ck. So let's put it right here. F of ck times the base. For this one, the base is xk minus xk minus 1. So let's put it right here, times xk minus xk minus 1. And once again, it keeps going until it gets to the last rectangle, which is this one right here, this rectangle. up to here. And the height of this last rectangle, of course, it's equal to function value at Cn, the last middle point. So I'm going to put it right here, f at Cn times the base. So the base is right here, xn minus xn minus 1. So I can add it right here, times xn minus xn minus 1. The next thing I'm going to do here is to name x1 minus x0 right here to be equal to delta x1. And for this one right here, x2 minus x1 to be delta x2, the change in x number 2. For this one, delta xk. And last one, delta xn. At this point, we have all these terms summed together, and it looks quite messy. What about we add them together and make it look nicer using sum or sigma? So let's have sigma sign right here. And the index would be k. Index is going to start at 1, the first term. And it's going to keep going. Increase to 2, 3, and ends at n, the last one. Stop at n. And now the first term that we need to include in here is the function value at the middle point, f at ck. So index k right here is going to start at 1, the first middle point, and then goes to 2, 3, and stops at n, the last term. And now the base, so we need to include this, delta x. And as you know, delta x is going to start at 1, goes to 2, and goes to k, and ends at n, which means that we need to include this index right here, delta xk. And once again, this k is going to start at 1 and stops at n. Now let's make a box around this. What you see right here in this box or up here is called Riemann sum. So let's make a note right here. Riemann sum. And it's actually the approximation of integral. So make a note right here, approx of integral. Now let me ask you this question. Based on what you see right here, is Riemann sum the estimation of the area under the function curve? So let me put the question right here. Is Riemann sum the estimation of area under fx? That is the question. And now the answer is yes and no. What kind of an answer is that? Both yes and no? How is that possible? Let's take a look here. This is going to be true under some condition, and it's going to be wrong under another condition. So let's take a look here. What you see right here in the sum is the function value, and we use this as the height of the rectangle. So what you see right here, this is the height, and delta x right here is the base, times the base. Of course, this is the area of the rectangle, but as you can see here, this function value, this f, can be positive and negative. For example, down here, f of x is less than 0, negative. But up here, the function value f of x is positive, greater than 0. But usually when we talk about area of something, it has to be positive. This one has to be positive. For example, the area of this piece of land is 2 square meters. No one says that the area is minus 3 square meters. That doesn't make any sense. So area has to be positive. So for this question, it's going to be yes when f of x is greater than 0. Riemann sum is going to be the estimation of the area under the graph when the function value is positive, so that we have the area that is positive. However, it's going to be a no when the function is less than 0. Because if you calculate Riemann sum, it's going to come out to be negative due to this negative value of f, and it's going to go to here too. Negative f, the sum is going to be negative. So keep this in mind. Riemann sum can be positive. can be greater than 0, and it can also be less than 0 if the function value is less than 0. And the last one, they can cancel each other, the positive part and the negative part. So make a note right here, can cancel as well. So underline this, very important. This can cancel. Now the next thing I'm going to do here is to change something in this box. The first thing is I'm going to make delta x equal for every section. So delta x, k equal to one value, delta x, for all k, which means that the width of the base of the rectangle is going to be equal for every section. So at this point, I'm going to get this. Sigma, same k equal to 1, stops at n, f of ck, same thing. But now delta x is right here, because every delta x is the same. At this point, I want you to take a look at these pieces. As you can see, the approximation is going to be bad because the rectangles are big. And we have all these errors. Overestimation right here, over right here, and some underestimation right here. Right here and right here. And you get the idea. And as you can see here, we have all these errors because of the size of the rectangle. And that is not good. So in order to reduce this error, we are going to make the piece smaller. So as you can see here, if we make it smaller, it's going to look better. And the error is going to be smaller as well. So the idea is to make it smaller, to reduce error. So smaller rectangles are good for the errors, and this means that making it smallest would be best. So we want delta x, the base of the rectangle, all of them, to go to 0, as small as possible. So we want to improve on this formula. We want to reduce the error from the Riemann sum. So this is our goal, reduce errors. And how do we do that? We make delta x goes to 0. So we have this sigma sign, just the same. Alright, and k starts at 1, just the same. And it's going to stop at n, just the same. And now we still have this function sign at the middle point, f at ck. Now times the base of the rectangle, delta x, and this one is going to be the same for every section. However, we still have this condition that we want to make it happen. Delta x goes to 0. What can we do? Well, we know limit, right? So let's put limit in. So it's going to be the limit of the same Riemann sum when delta x goes to 0. So delta x here is going to be really small, approaching 0. And as you know, when delta x is really, really small, we call it differential x. So this is going to be dx. So this is going to become dx. And the next thing that we need to know is that when delta x is really small, then we have so many pieces of the rectangles. As you can see here, more rectangles to consider. However, when it goes to 0, then the number of the rectangles would be infinitely many. So make a note right here. Infinitely many rectangles when delta x goes to 0. This means that n right here is going to go to infinity. We have so many of them. And now let's transform this limit further. What you see right here is a function value. And since ck is going to include every single point on the curve, so this is going to become f of x. And now the most important part. I'm going to put everything together down here. The first term, function value at x at all the points. First one, f of x, times the second term, back here, differential x, dx. Now I still need to include all these signs down here. But before that, let's take a look at the meaning of this. The meaning of this is that we are going to sum infinitely many small pieces together. Alright? So we have sum, and it's going to be infinitely many. Infinity. And then each piece is going to be so small, infinitely small. The meaning of this is integration. Integration is combining things together. So what we have right here is basically the integration sign. And I can put it down here. It looks much nicer this way. Integration of the function value times dx. The meaning of this is still quite similar to what we have before. The height of the rectangle times the base of the rectangle. And we combine them all together, except that this time each piece is so small, and we add this infinitely many pieces together. And don't forget that this integration starts at x equal to a and ends at x equal to b. Let's make a box around this. What you just saw right here is the derivation of definite integral. Make a note. This one, definite integral. And it actually came from Riemann Sum, except that it's the improved version of that. Now let's move on to the next slide.